It's pretty wild, right? Like all these incredible tech advancements we see popping up, it often feels like they just appear out of thin air.
Yeah.
And
Fair.
then when you dig down, look under the hood at what's making all of this possible, at the foundation of it all, you find this story of constant progress, the semiconductor industry. It's like this relentless, one step at a time kind of thing where each tiny gain builds on everything that came before, over like, what, 50, 60 years.
Yeah, absolutely. And the International Electron Device Meeting, or IEDM, that's where the people pushing those boundaries, the ones driving all of that progress, they get to show their hand.
Right. It's like their annual unveiling, like, hey, this is what we've been up to. This is what's coming next.
Exactly. It's the place to see the bleeding edge of chip research. You get the most cutting edge findings, the newest ideas, and everyone dissects them, debates them. So for this deep dive, you sent me a ton of reports and analyses from the latest IEDM, and we're really going to zero in on the key stuff, the crucial advancements in logic.
Logic, the brains of the operation.
Exactly. And then there's memory, where all the data lives, and this increasingly important area of how all these intricate pieces are actually put together, which is, of course, packaging.
Right. So, how do we cram all that amazing tech into a tiny chip?
Right.
And really, the big question we're going to be tackling here, for you listening, is whether all of this incredible innovation in semiconductors, all this amazing stuff, can it actually keep pace with the demands of AI?
Yeah, the demands are off the charts.
Absolutely. It's like AI is this hungry beast that just wants more, more, more. We've got this stack of IEDM intel here, so our mission is to break it all down, figure out what's really important, give you a clear picture of where chip tech stands today, in the face of this AI revolution. Where are we now and where are we headed?
That's the plan.
All right, so let's dive in. First up, the basics, the building blocks, logic.
So what really stood out was TSMC. They're still pushing the limits in advanced logic. Their N2 process, which they're going to roll out soon, was a big highlight at IEDM. It's their first foray into gate-all-around transistors, GAA, and the performance they're claiming, pretty impressive, like a 15% speed boost or 30% less power consumption. And they're packing in over 1.15 times more transistors in the same area.
Which is the holy grail, right? Faster, less power hungry, and smaller, all at the same time.
That's the goal.
They also made a big deal about N2 having 6 different threshold voltage levels, VT2. For someone who isn't designing chips, why should they care about having a bunch of different VTs?
Okay, so think of VT as like a sensitivity dial for a transistor. It controls how easily it switches on and off. A low VT transistor, it's super sensitive, switches really fast, which is great for speed, but it also tends to leak a little bit of current even when it's off.
Ah, so that means more power consumption.
Exactly. Now, a high V transistors, it's less sensitive, switches slower, but it hardly leaks any current, so it saves power. Having 6 different VTs gives chip designers more control, more fine-tuning options. Like, a high-performance core in your CPU might need those fast, low VTs transistors, while other parts of the chip, where speed isn't as crucial, they can use the power-sipping high VT ones.
Okay, I get it. Like having different gears in your car for different situations.
Exactly. You want the right tool for the job.
Now, one thing they mentioned was that with these new GAA transistors and the different VT levels, it gets tricky depositing the dielectric material around the gate. That sounds pretty technical.
Yeah, it is a bit. But the key is, in GAA transistors, the gate, which controls the current flow, it's surrounded by this insulating material called the dielectric. With this design, it's harder to get an even coating, with the exact thickness you need for each VT level, because you don't have a direct line of sight. That's where atomic layer deposition, ALD, comes in. It's a super precise method, like applying material one atom at a time. You need that level of control to get those different VTs working reliably.
Okay, so like atomic level spy painting. Super precise.
Basically.
And they didn't just improve the transistors themselves, right? They also talked about the interconnects, all the wiring between them.
Right, the interconnects are crucial. They're like the highway system connecting all those billions of transistors. TSMC showed some impressive gains there. Their new barrierless tungsten gate contacts, probably using some cutting-edge equipment, led to a huge 55% reduction in RC.
RC, meaning
Resistance and capacitance. Resistance is like friction, slowing down the signal, and capacitance is like having to charge up each wire before the signal can go through. Lowering both means signals travel much faster. They actually showed, in a test circuit, over a 6% performance boost just from this interconnect upgrade.
wow, so that's a significant speed bump just from better wiring.
It makes a big difference.
And it wasn't just the gate contacts, was it? They also talked about improvements to the actual metal layers themselves.
Yeah, for the main metal layers, the ones they use the most, and the vias, which are the vertical connections between layers, they managed to reduce RC by 19% and 25%, probably thanks to better insulating materials between the wires. But here's where it gets really interesting. They unveiled a new way to pattern the M1 layer, which is one of the densest and most critical ones. They're using this 1P, 1E EUV technique. It's basically a super precise way of printing the chip layers using extreme ultraviolet lithography. This specific method is pretty clever. It lets them get more detail with fewer steps. And with this, they managed to reduce the capacitance of that M1 layer by a whopping 50%. And on top of that, they even saved multiple expensive EUV masks in the process.
So that's a huge win-win, lower costs and better performance. And it emphasizes their point that future progress isn't just about making things smaller. Materials, innovation materials, that's going to be just as important. And you mentioned that TSMC was basically the only big player presenting their, 2nm class GAA
Yeah,
tech.
2 nanometers, give or take.
So what about their competitors? What do we hear from, say, Intel, Samsung, and others? Well, the fact that Intel, Samsung, even Rapidus, aside from this one specific paper from Rapidus on fine-tuning VT, the fact that they didn't present anything on their comparable next-gen nodes suggests they might not be as far along. TSMC seems confident enough to showcase their N2, while the others might still be ironing out some kinks.
Interesting. So GAA is the state of the art for logic right now. But what's next? What's on the horizon? We've heard whispers about this thing called CFE.
CAA, which stands for Complementary FET, that's the big bet for what comes after GAA. The idea is to stack a PMOS and an NMOS transistor right on top of each other, vertically, instead of side by side like they are now. This stacking is what could give them another density boost, something like 1.5x, compared to the traditional layout.
So squeezing even more transistors into the same space sounds clever, but I imagine actually building these stacked transistors can't be easy.
It's a huge engineering challenge. There are a few major hurdles. First, you're basically doubling the vertical complexity. Second, you have to build that top transistor without messing up the one below it.
Right, like stacking a house of cards on top of another house of cards.
Exactly. And then third, you've got to figure out how to efficiently deliver power, and potentially even signals, to the back of these stacked transistors. That often means direct backside connections.
So it's not just stacking them up, it's making sure they can all talk to each other and function properly. You mentioned some different approaches being explored for these CFETs.
Right, so IMEC, they're a leading research center. They presented a concept for a 4T CFEO cell that uses these shared connection points and a backside power delivery network. They're focusing on simplifying the process of making those source and drain contacts by using a shared middle routing wall. It's an interesting idea, but so far, it's all simulations.
Okay, so theoretical for now. What about Samsung and IBM? Did they have a different approach?
They showed off a stepped CFET design. It uses 2 wider channels in the bottom NFET and 3 slimmer channels in the top PFET. This gives you a more direct path to connect to those bottom channels when you're forming the contacts, which could improve electrical performance. But the trade-off might be density, how tightly you can pack these transistors. Those wider channels might take up more space compared to designs with shared power connections or backside routing.
So different strategies, each with pros and cons, but it sounds like TSMC might be ahead of the game here too.
It seems like it. TSMC actually demonstrated a working CFS inverter, the most basic building block of digital logic. It's a stacked PMOS and NMOS transistor. What's significant here is that they went beyond simulations. They actually fabricated and tested this on a real silicon chip. And crucially, they have a method for creating that local interconnect between the top and bottom transistors, which is something IMSeq was still figuring out in their simulation.
So they've got a working prototype. That's huge.
Yeah, but it's still early days. The performance looks promising, but the sheer complexity of building these structures with those really tall, thin features and needing incredible precision during manufacturing, those will be huge hurdles to overcome if they want to get good yields in high-volume production.
Right. It's one thing to make one work in the lab. It's another to crank them out by the millions.
Exactly.
All right, so that's a glimpse into the future of logic. Pretty fascinating. Moving on to memory, the challenges there, especially with AI, are just as interesting.
For sure. The memory landscape is changing rapidly. Everyone's talking about high bandwidth memory, HBM, which is essential for feeding data to those powerful AI accelerators.
Right, HBM is the hot topic.
Yeah, but it's such a commercially sensitive area right now that we didn't get any real technical details at IEDM. Nobody wants to give away their secrets.
Makes sense. Keep your cards close to your chest.
Right. So the real focus in memory innovation was on compute in memory, CIM.
Compute in memory, so processing right inside the memory itself.
Precisely. The main bottleneck in a lot of computing systems today, especially with those massive data sets in AI, is the memory wall. It's the gap between how fast processors can crunch numbers and how fast they can get that data from separate memory chips.
Right, the data has to travel, and that takes time and energy.
Exactly. So moving data back and forth between the processor and memory, it's a huge drain. CIM aims to break this wall by bringing the computation closer to the data or even doing the computation right inside the memory cells.
So less data travel, less energy wasted. Sounds like a game changer for AI. What kind of approaches are we seeing in this compute and memory space?
SK Hynix presented this cool architecture called AIM, Accelerator in Memory. They basically took standard GDDR6 memory, the kind you find in graphics cards, and added a processing unit right next to each memory bank. The results they showed were impressive, like 2 orders of magnitude higher memory bandwidth per gigabyte compared to even the best HBM.
2 orders of magnitude. That's a crazy improvement. So why isn't AIM technology everywhere already? What's the catch?
The main limitation right now is flexibility. Those processing units they integrated, they're probably highly specialized for very specific calculations. The best near-term applications might be in on-device AI, things like augmented reality, where you need super low latency for things like hand tracking.
So really fast, but for specific tasks, not a general purpose solution yet.
Right.
What other interesting work was happening in compute and memory?
Meta, the company behind Facebook, they presented research on both compute near memory and true compute in memory. For compute near memory, they explored 3D packaging, basically stacking SRAM or DRAM directly on top of the processor. They saw pretty significant reductions, around 40%, in both the delay and the energy needed to access memory just by stacking SRAM this way. And they project even better results for a mix of SRAM and DRAM in this stacked configuration.
So shorter distances, faster data access, lower power consumption. Makes sense. What about their more direct compute and memory efforts?
They proposed a CIM design that actually integrates logic gates, the things that do the calculations, right within the memory arrays. Their simulation suggests this could potentially double the energy efficiency of AI accelerators.
Sounds promising.
It does, but there are some serious hurdles. Reliability and accuracy are big concerns for a lot of CIM architectures. For example, if you try to repurpose DRAM cells, which are meant to store data, to also do logic operations, you tend to get a lot more errors compared to dedicated logic circuits.
Right, memory is built for storage, not necessarily for computation.
Exactly. And there are also fundamental differences in how you manufacture DRAM and logic chips. DRAM processes involve higher temperatures, which makes it tricky and expensive to combine them. And even for the compute near memory approaches, which use advanced packaging like hybrid bonding, like what we've seen with AMD's stacked CPUs, the cost is still a big barrier.
So it's a promising area, but lots of challenges to overcome.
Definitely. But the need for more energy-efficient AI is so huge that we're going to see a lot more research in compute and memory.
Okay, so we've got logic and memory, both pushing the boundaries. Now let's talk about how all these pieces are actually put together, literally, with advanced packaging.
Packaging is becoming more and more important because we're hitting limits on how much we can shrink features on a single chip.
Right. The good old days of Moore's Law are slowing down.
Exactly. So advanced packaging is a crucial path forward. It's how we're going to keep increasing computing power and integrate these complex systems.
And there are so many different terms thrown around with packaging. What were the key takeaways from IEDM?
So Intel gave an update on their EMIB technology, and they announced EIB-T. The T stands for Through Silicon Vias, TSVs.
Okay, so TSVs, those are like tiny vertical tunnels that go through the silicon.
Exactly. EMIB uses these silicon interposers, think of them like small, passive silicon chips embedded in the larger organic substrate. They allow for much higher interconnect densities compared to just using traditional substrates.
It's like a denser, more efficient way to connect everything.
Right. The original EMIB used these interposers but didn't have TSVs, probably to keep costs down.
So why add them now with EMIB-T? What's the advantage?
Well, without TSVs, some of the signals and power had to be routed around the interposer. Adding TSVs gives designers more flexibility. They can route everything, signals, power, right through the interposer. And as TSV manufacturing has matured and become cheaper, eMIBT becomes a more appealing option for high-performance computing and other applications that need a ton of interconnects.
Right, so more options, more flexibility. And I imagine this ties into their other packaging technologies, like Foveros, their 3D stacking approach.
Yeah, exactly. They're aiming to combine these different technologies, 2.5D with EIB and full 3D with Foveros, to offer a range of interconnect densities for different applications.
So it's about having the right tool for the job, just like with those VT levels and transistors.
Exactly.
What about TSMC? They're also doing a lot of interesting stuff in advanced packaging.
TSMC presented an update on their SOIC technology, System on Integrated Chips, which uses 3D packaging. While Sony is leading the way with hybrid bonding for image sensors and cameras, TSMC seems to be at the forefront of applying it to advanced logic chips. Their latest SOIC generation seems to have an interconnect pitch of less than 15 micrometers.
Interconnect pitch, meaning.
It's basically the distance between those tiny connections.
Yeah.
And just for comparison, Intel's Foveros is around 25 micrometers.
So TSMC's connections are closer together.
Yeah, and that's a big deal because the density of those connections, and therefore the performance, it scales roughly with the square of that pitch.
So a small difference in pitch leads to a big difference in performance.
Exactly. These advancements in SOIC are enabling much tighter integration and better performance for designs that break down a big chip into smaller chiplets that are then interconnected very densely.
It's like building a supercomputer out of Lego blocks.
Kind of, yeah.
NVIDIA also had a presentation that touched on system co-optimization. What was their main takeaway in the context of packaging?
NVIDIA highlighted something that often gets overlooked, defect density. We always talk about the exponential increases in things like transistors and computing power, but they pointed out that the number of defects, tiny imperfections, that happened during manufacturing. That has to decrease at a similar exponential rate if we want to keep getting decent yields as we move towards chips with trillions of interconnects.
Trillions of connections, and every single one has to be perfect.
Pretty much, yeah. One defect out of a trillion, that's an incredibly low defect rate.
It's mind-boggling. And it shows just how incredibly precise and controlled every step of chip manufacturing has to be.
Absolutely. It's a testament to the constant improvements being made in the processes, the equipment, the materials, all those things we don't usually see.
It's the unsung heroes of the tech world.
For sure.
Now, it's also worth considering what wasn't presented at IEDM. Sometimes the things that are missing can be just as informative.
Definitely. One notable absence was CXMT, a Chinese memory maker. Last year, they presented details of a DRAM process that seemed to be violating sanctions, and this year they were nowhere to be seen. It probably reflects those tighter export controls that now seem to be affecting their more advanced 18.5 millimeter process.
Yeah.
And overall, there's a much smaller presence from Chinese companies, with more presentations coming from universities.
Right, so the geopolitical situation is definitely having an impact. Were there any interesting technologies from last year that didn't make a return appearance?
Yeah, Micron's NVDRAM, which was pretty exciting last year because it promised DRAM-like performance with non-volatility, meaning it could retain data even when powered off. That wasn't presented this year. It hasn't been commercialized, and the fact that it didn't show up at IEDM suggests there might be some significant hurdles, maybe related to cost or scaling it to high volumes.
So sometimes those promising research projects hit a wall when it comes to real-world production. Now, looking further ahead, there's been a lot of talk about using 2D materials to replace silicon in transistors. What was the latest on that front?
There's a lot of excitement about 2D materials like molybdenum disulfide, OS2 for N-type transistors, and tungsten disalign, WSE2 for P-type transistors. These materials have extremely thin channels, which could potentially let us make transistors with much shorter gate lengths than what we can do with silicon, which is starting to hit a wall around 10 nanometers due to leakage. But getting these materials ready for mass production is a long way off. Intel highlighted three main challenges: growing these materials in large, high-quality sheets, controlling their electrical properties through doping and making good contacts, and then building that gate-all-around structure with a high-quality insulator around these 2D channels.
A lot of challenges, but it sounds like there's some progress being made.
Yeah, we are seeing some encouraging results, particularly in doping and contacts. TSMC showed some work on making reliable contacts for P-type devices, using this technique called degenerate doping, which is important because making good contacts to N-type 2D transistors had already been demonstrated. But getting uniform doping across the whole material is still a big hurdle. Intel also showed progress in making high-quality gate oxides, the insulator, for these 2D materials. This led to much better electrical control of the transistor. But the big one, the really tough problem, is still being able to grow these 2D materials directly on standard 12-inch silicon wafers, which is crucial for mass production. Samsung had presented some work on an 8-inch wafer, but it doesn't look easy to scale that up.
So lots of individual pieces are coming together, but putting it all into a manufacturable process, that's the real challenge. TSMC even presented a study on building a full logic gate, a 2D FET inverter, didn't they? What were their key findings?
They did, and the results really show how complex this is. They found that using the same 2D material, WSE2, for both the N-type and P-type transistors in the inverter led to poor performance for the N-type device. This suggests that using different materials for NMOS and PMOS, which is more complex, might be necessary. And they also found that standard wet chemical processing, which is commonly used in silicon chip making and generally doesn't affect traditional transistors, it actually significantly changed the threshold voltage of their 2D PFETs.
So there's still a lot to learn about how these new materials behave in a real manufacturing environment.
Yeah, it's not as simple as just swapping out silicon. And meanwhile, silicon technology is still advancing.
Right, it's not standing still.
Exactly.
Yeah.
Intel showed off a working single-ribbon GAA transistor with a 6-nanometer gate length. This is a big deal because it challenges the idea that silicon can't go much below 10 nanometers due to quantum tunneling, where electrons can leak through the gate. Intel's demonstration shows they can manage this tunneling, and the transistor's performance is already pretty good.
So silicon still has some tricks up its sleeve.
Yeah, it seems like it. And this likely pushes the need for 2D materials even further out, because as long as they can keep innovating with silicon, chip makers will probably stick with it.
Makes sense. It's less disruptive. And all of this progress is happening against a backdrop of skyrocketing demand for compute power, largely driven by AI. This led to a pretty stark warning from an expert panel at IEDM, didn't it?
Yeah, Professor Tom Lee from Stanford, he presented these projections of the energy demands of future computing. He basically said that if things keep going the way they are, by 2050, the energy needed to power AI could be as much as all the solar energy that hits Earth in a year. And by 2150, it would exceed the sun's total energy output.
Wow, those are some sobering numbers.
It's meant to be a thought experiment, but the message is clear. The energy consumption of AI is going to be a huge problem unless we have major breakthroughs in efficiency. As Professor Lee put it, we can't defeat an exponential foe with linear swords and sticks.
So incremental improvements might not be enough. We need something more radical.
That's the takeaway.
So to sum up our deep dive into IEDM, we've seen continued progress in logic with TSMC's N2 and the ongoing efforts to make CFTs a reality. In memory, the focus is shifting towards compute and memory, but with lots of challenges still ahead. And advanced packaging is becoming crucial for pushing performance and integration further.
And the big picture is this tension between all the amazing progress in semiconductor tech and the even faster growing demands of AI. That warning about energy consumption really highlights the need for more fundamental breakthroughs.
Absolutely. So here's a final thought for you listening. Given these limitations and the energy challenge, how will our approach to computing and AI have to change in the coming decades? Will it be enough to just keep cramming more transistors onto a chip? Or will we need equally big changes in the algorithms and the architecture of our systems, the way we process information at a fundamental level? It's a question that goes way beyond silicon. We encourage you to dig deeper into these topics and think about the implications. Thanks for joining us for this deep dive.
Thanks for having me.